All right. So let's have a little squiz at this question over here. Question 5, so this is a question on logistic model. It says Georgia decides to put 6 goldfish into her newly built pond. Okay. So what do we know in this question? We know that P0 is equal. Let's start by writing down what you know. So P0 is equal to 6. Okay. 1 year after introducing the goldfish, the population has grown to 11. So in other words, they're telling us P1 is equal to 11. Okay. A goldfish expert informs her that the carrying capacity of the pond is 30. So K is equal to 30. And the population grows according to the logistic model. Determine how many years it'll take. Okay. So N is equal to question mark. That's what we're asking. For the population of goldfish to reach its carrying capacity. In other words, when it's Pn equal to going to reach a value of 30. Okay. So it's a logistic model question. So we go to your formula sheet, okay, and we have that P to the N plus 1. We just copy it down straight from your formula sheet. And P to the N plus 1 is equal to Pn, okay, plus Rpn 1 minus Pn over K. Now, the problem is we don't know what R is. So we have to go figure out, okay, what R is in order to figure this. I can't go figure out P when the population is going to be 30 if I don't have a model for that. Okay. So the first objective is to figure out what R is. So to do that, I'm going to use the fact that P1 is equal to 11 and that P0 is equal to 6. And then we're going to use a logistic formula, which if we replace N with 0, we have P1 is equal to P0 plus Rp0, 1 minus P0 over K, and K is equal to the carrying capacity is 30, right? Okay. But we know that P1, they told us population after 1 year was 11. So 11, and they told us that P0 is equal to 6. So 11 is equal to 6 plus R times 6, 1 minus 6 over 30. Okay. So if you go, so 5 over 6 is going to be equal to R 1 minus 6 over 30. So take 5 over 6 in the calculator, divide it by 1 minus 6 over 30, and you should end up with an answer of R being equal to 25 over 24, okay, which is 1 comma something. So that is your intrinsic growth rate for this particular logistic model question. Okay. So now we have a formula for this particular population, and that is Pn plus 1 is equal to Pn plus 25 over 24, 1 minus Pn over 30. We also know that P0 is equal to 6. So on your calculator, what are we going to do? We're going to go 6 equals, clear it. Okay. So now 6 is stored on your calculator. Then wherever you see Pn, okay, you're going to press your answer button. So you're going to go answer plus 25 over 24, 1 minus answer over 30. You press it once, okay, and you should get P1. Always write down P1 just to show the mark you're on track. So P1 is equal to 11. You keep pressing, and eventually, not much longer, P5 is equal to 30. So in other words, it takes 5 years for the population of the goldfish to reach carrying capacity. Okay. Right. Then the next question, which is a common question. So it says here, okay, I filled in the latter values, but I'm just going to explain the first two things that you get. The spread of virus in an animal over a week is given by the following table below. So after 0 days, okay, there were 7 million cells in the animal. After 1 day, there were 12 million cells. After 2 days, there were 18 million. And after 3 days, there were 27 million. Okay. We've got the next question says complete the table. Okay. Over here in this question, on the given table, calculate delta P and blah, blah, blah. Okay. So that's the question. So we have to complete that table correct to 5 decimal digits. Okay. So this concept of logistic growth rate, which this is your logistic growth rate over here. Okay. Delta P over P represents your logistic growth rate. Okay. Delta P, you can think about as the average gradient around the point. Okay. So if we were looking for the logistic growth rate around the point 112, on average, how is this thing changing? Okay, remember, logistic growth rate is a function of population. That's why we divide by this value P over here. So we want to know, on average, what's going on around this point. So in order to calculate a logistic growth rate, you need to know the value before and the value after that point. Okay, so I've got the value before, I've got the value after. That's why I cannot find a logistic growth rate. That's why this is shaded in, because I can't find a logistic growth rate around the 0.07 because there's no value before that. Okay, likewise with the last one, there's no value after that. So the first place I can find the logistic growth rate is the logistic growth rate around the 0.112. So what is logistic growth rate equal to? It's equal to average gradient around that point. So what is an average gradient? The average gradient between these 2 points is change of y over change of x. So it's 18 minus 7. Okay. The change of x in this particular scenario is always going to be 2 because 2, it's around the point. So it's over 2. So it's 11 divided by 2, which is equal to 5,5. Okay. That's your average gradient, but they want the logistic growth rate. So the logistic growth rate is the average rate of change divided by the function of population, which is 12. So you're going to go 5,5 divided by 12, and you get an answer of 0,45833. So that is the logistic growth rate around this point over here. If I look at the logistic growth rate around point 2, so around this point over here, well, I have the value before, which is 112. I have the value after, which is 327. So I'm looking for the gradient. The average gradient around that point is the average gradient joining those two, the two endpoints. Okay, but the gradient around the two endpoints doesn't have to go through the middle point. So here, the logistic growth rate around point 2 is going to be the average gradient around point 2. So your logistic growth rate is going to be, so over here, sorry, around point 1. Okay, it's going to be delta P over B, your average gradient over P, and your average gradient was this 18 minus 7 over 2 divided by the population, which was 12. So it's 18 minus 7, the change of y, okay, over change of x, which was 2 divided by 12. So the logistic growth rate around point 2, day 2, I'm going to just go straight to the table, is going to be equal to, make that a bit bigger. Logistic growth rate around this point is your average gradient, which is change of y, which is 27 minus 12 divided by 2, which is 15 divided by 2, which is 7,5. And then it's your gradient as a function of your population in the middle, and your population in the middle is equal to 18. So you get 7,5 by 18, which is 0.41667. So logistic growth rate, average gradient around that point, doesn't even have to go through the point, average gradient around that point divided by the population in the middle. Okay, there's your average gradient, there's your logistic growth rate. It's a function of population. Okay, I filled in the rest of the values for you. You can figure those out. So now I've got that whole table of values. Okay, so now it says uses. So what you end up with? Okay, if you take the values of X and Y, remember you've got this scenario over here. In the logistic model, if you plot the graph of delta P over P, in other words, the logistic growth rate as a function of the population, okay, right? Not a function of time, as a function of the population. Don't confuse it with this growth path over here, which is time and population. Right, what it generally generates is a straight line, okay, with the maximum logistic growth rate is your intrinsic growth rate, and the maximum population is your carrying capacity. Remember, your maximum in the logistic model, your maximum population is your carrying capacity, and in the initial growth rate is your maximum growth rate, which is your intrinsic growth rate. So now it says use a statistical mode of your calculator, determine the equation of the line of best fit to 5 decimal digits for delta P over P against P. So you're plotting delta P over P, okay, against population. So population is on your X. So population is your X values. Your Y values is your logistic growth rate, which is delta P over P. So on your calculator, you're going to go mode, that mode, set the line of, so you're going to go mode, stats, it's number 2 on my calculator. Okay. Then you're going to go, okay. So I'm sorry, mode, stats, right? And then you get your options, right? And the option we want, okay, we want to find a line of best fit. So we're going to press whatever on your button on your calculator is. We're going to go A plus BX. On my calculator, button number 2. And then you're going to get a column. This column is going to appear X and Y. So X is P, Y is delta P over P. So the first value is going to enter, well, I always enter columns, but anyway, so you're going to go 12 and you're going to have that. I always enter all of those, and I come back and run that. So enter all your P values, enter all your delta P over P values next to each other. Okay. Once you've entered them, okay, you clear your screen. So you enter your data, X and Y, P and delta P over P. Okay, then you clear your screen. Then you got to say, what am I going to do with that information? To access information in stat mode, you go Shift 1. Okay, right? And then you are looking at regression. So then you're going to press the regression button, option. So regression. Okay, my calculator is number 3. Okay, right? And then you're going to have the option, okay, sorry, Shift, setup, regression. And then you want to figure out, okay, so that in this model over here, okay, so it says determine, using the stat mode of a calculator, determine the equation of the line of best fit. So we're going to have the line of best fit is normally written in this form, y cap is equal to a plus bx. Okay. In this case, if you think of it as y is equal to mx plus c, okay, we're going to have the y values are delta p over p, okay, is equal to a plus b. Your x values are p, right? The delta p over p is going to be a plus bb. Okay, you want to write it in that format. Okay, y is equal to a plus bx. So if you go and press number 1, you get a. On your options button. So you go 1, a equals, and you should have got a is equal to 0.84003, and you should have got b. You clear your screen, you go back into the menu, and you should get b is equal to negative, and you expect a negative gradient, negative 0.07209. Okay, so your equation of your line of best fit, you either leave it in y and x form or this form. You're going to have delta p over p is equal to a, which is 0.84003, plus b, so in other words, minus 0.07209. 209p. If you wrote it as y is equal to that minus that x, that's also fine. So that, okay, is your link between delta p over p and p. So on our graph, this particular, what we figured out for this particular population model, the equation of this line is this, which looks kind of right. There's the equation of the line. Okay. Now remember, here's your logistic growth rate, here's your population. Your maximum logistic growth rate is R. So your y-intercept of this line is R. Okay, and the x-intercept is your carrying capacity. So you can find R and K just using intercepts. So R is equal to the y-intercept. So in other words, R is just the constant value, and that looks right. So R is 8,4003. Always think of this graph in your head. Okay. And K, if you know the equation, is equal to the x-intercept. So if you solve naught is equal to 0.84003 minus 0.07209, well, the carrying capacity there is K. You end up with K is equal to 11,65252. 65252. That's your maximum carrying capacity. Curious to see something? Right. Okay. So there's your carrying capacity. Okay, 11,65252. What links them up? Remember, if you ever have to link them up, your gradient is change of y, which is negative r. You're going in that direction over k. Right. And so you can also use that in order to find those parameters. All right, guys, that's logistic model.